No big deal. I'm so ready to get that stuff on my roof. You too, why? Okay. Shoot, what have we been talking about? Been a while, huh?
Spontaneity gives free energy.
Yes.
All that jazz.
Turn to page 784. Okay. I'm just going to read the first paragraph of 17.7, and then we're going to get into how to do equation. Okay? This should be a relatively short lesson. Hoping we'll get done in like 20 minutes. All right, in this chapter we have seen that a system at constant temperature and pressure will proceed spontaneously in the direction that lowers its free energy. This is why reactions proceed until they reach equilibrium. The equilibrium position represents the lowest free energy value available to a particular system. The free energy of a reaction system changes as it proceeds because free energy is dependent on pressure of a gas or on the concentration of the species in solution. We will deal only with the pressure dependence of a gas. The dependence of free energy on concentrations can be developed using similar reasoning. So what we're going to focus on in this particular lesson is specifically gas pressure. And I don't know if you guys remember, but we can do an equilibrium constant with pressure. Do you remember that? There were two expressions. There was an expression where we used concentration, probably the one we're most familiar with, right? But we can also find the equilibrium constant using pressure. Do you guys remember that? Okay, so we're going to deal with the pressure dependence here. Okay, and I think, is it highlighted, that one sentence at the bottom of 794? Is it highlighted? Yeah, it is. Okay, that's important. So really, what equilibrium is, when I say something is at equilibrium, that's where it's at its lowest free energy possible. So if that's the case, if I'm at equilibrium, what is the change in G? Zero. If I'm at equilibrium. This is why if I say change in G is some negative number, this means it's not at equilibrium and it has to lose 1,000 kilojoules of energy to reach equilibrium, and usually that is a spontaneous favorable direction. Okay? It's like I'm at the top of the mountain and I gotta go down the mountain to reach equilibrium. It's gonna happen spontaneously. Does that make sense? If I say my change in G is positive, that means I really have to go up the mountain to get to equilibrium. And it's not going to be favorable or spontaneous. Does that make sense? Okay? When I am at zero, that means I'm at the lowest point of energy for a particular system. And that's when you have a change in G of zero, which we'll see that as we progress today. Okay? This is actually the start of, eventually we will start throwing in K here, and we will start doing some stuff. Obviously Q is a certain position. It can be the equilibrium if the K and Q are equal. Do you guys remember, if K and Q are equal, you're at equilibrium. If Q is greater than K or if Q is less than K, then it's going to shift left or right depending upon which it is to get to equilibrium. So we're kind of starting that process today. So we are going to solve for Q using pressure. Okay, temperature is again in Kelvin, we're pretty familiar with that. I don't know if we've used this R value. Have you guys ever used that R value? We could use the other R value, 0.0821, but this is the R value that has energy in it, so that's why we're using that one. It's basically equivalent to the other R value, just different units. Does that make sense? I could get this to turn out to be 0.0821, switching units around. Right. But for the amount of work that's going to take for the value of it, I'm not going to show it to you. Okay? This specifically is dealing with the change of free energy of your entire reaction, standard. Okay? And this is at a certain pressure. So obviously, this is going to go up or down depending upon what pressure it is. Under certain pressure situations, it's going to be more spontaneous or more favorable, and in other conditions, it may be less spontaneous or less favorable. That is if we're at equilibrium. Got it. Yeah. So, what was I going to say here? I don't know if you guys remember, but that little degree symbol means standard conditions. Right, what did we say standard state was?
25 degrees Celsius.
180. Okay, so this would be what the G would be if the pressures were 1. And we're going to figure out if I increase the pressure, if I decrease the pressure, is it more spontaneous or less spontaneous, essentially. Okay. Set. Gave you the equation here. There's our equation. This would be what the change in G would be if my pressures were 1. We're going to use pressures that are different than 1, so we're going to have a Q that will change. And we're going to see at a pressure of 5 and 3, is it going to proceed further to the right or not? More spontaneous or not? Okay? So the very, very first thing we should probably find is this. If you remember, there are 3 ways to find it. Okay? There was an extremely long way. Which way was that? Let's just review that. That's probably a good thing to review. What was the really long way to find change in G? Yep. Yep. Now, could we look in the back of the book, find the change in H, find the change in S, plug in and find the change, and that's the change in G prime. Under all those numbers in the back of your book are at standard state. Does that make sense? Okay? There was another method. There's 2 more. Okay? That's probably the easiest one. That's the one we're going to use. And the third one, they didn't give us enough information to even use the third one, but do you remember which method that was? What'd you say? Yeah. So you're on the right track, but it's called Hess's law. Oops. Ah! I did it again! Okay? So, this one is probably the one that's used the most. This is the easiest, and this is the one that's probably used the least because it only works if they give you the steps or the reaction mechanism.
It's pretty easy to know it's the third one.
Yes, it'll give you the steps. Okay? And then determining whether you use this one or this one is based on what information they give you. If they give you the H information, S information, but don't give you change in the G information, then you got to use that one. But if they give you the G values, like on a test, I may give you H and S, and you got to use the first one. Or I could give you just the G values, products minus reactants, and then you would use that one. Okay? But for simplicity purposes, let's just find change in G using the second method here. Products minus reactants. So jump to the back of your book here. You're just gonna wait for everybody else to do your work. I know, that's how Emily works.
Just final math initial, so it's CH2OH.
Yep, so your first guy's gonna be liquid methanol.
G is negative 166.
So I got 1 mole of it. Negative 166. It's kilojoules, right?
Kilojoules per mole.
Okay. Minus 1 mole of CO2. What's the number?
CO. One more
CO, sorry. Did I say CO2?
Yeah. Negative 137.
Yeah, I'm guessing this is 0, but just,
H2 gas.
yeah.
203. This is H.
For G,
No, that's H. That's H2 gases.
it should be 0. Because this is naturally occurring,
Is that G? Is that changed to?
we want to change the G,
Yeah.
the G value.
203.
That's S. That's H1 gas.
H2.
You're on H. Okay, this is going to be, I'm pretty confident that I know for a fact that when you have your H values, when you're talking about lone atoms or individual elements, it's 0, right? Because that's naturally what it occurs in. Okay, so the change in G is probably going to be 0 also for the same reasoning. It's naturally occurring that way, so it'll already be at equilibrium. So G is going to be 0. So we'll just put that there. And you do the math. Should be a little bit negative, right? Okay, negative 29. Let's see, don't want to. Our R in our equation was in joules, right? So we should probably get that to joules. Right? Okay. All right, so our R right? 3, 1, 4, 5. That's probably not too much. Okay, temperature, so you gave us it. Okay. So it's still at standard temperature, but it's not at standard pressure, correct? And we gotta find Q. How do we find Q? Yep. So let's just write the expression first. Well, this isn't going to be anything because it's not a what. It's a liquid or liquid or solids are 0, but it's not going to have any pressure because it's a liquid anyways. So what?
Just 5 times 3.
Isn't it
Well,
1 over or 1 divided by 3 times 5? That makes sense, everybody? I didn't write what? Products minus reactants, so I can't not have the 1 here, right? Because then it would be on top instead of on bottom. Yeah, you guys want me to write the expression?
But wouldn't it be, so wouldn't the 3 be squared? It's 2H2.
What?
It's 2H2 with it be 9 times 5?
Oh, Yep, we need to, which one is hydrogen? 5?
No, carbon monoxide is 5.
Oh,
So it's 9 times
there? Is that what you guys were looking at me funny like?
5.
So this would be 1 over the pressure of H2 squared times the pressure of CO. That would be your equilibrium expression. That's when you plug in your numbers. What'd you get for Q though?
Oh,
0.022. So what did you get for the change in G at a higher pressure?
38,431.
Okay. Let's try to make sense of this here. Let's compare the G values, the G value at an increase in pressure from the G value at standard state. What was the G value at standard state? 2900, right? And this is the G value under the increased pressure. What can you say about increasing the pressure? What does that do for the reaction here? Okay, decreases G, but does that mean it's going to proceed further right or further left? Further right. Because I have to lose this much energy versus this. This is a more favorable further right under these pressure conditions. Now, let's try to connect this to something we already know. Okay? Le Chatelier's principle. Do you remember that? When you cause a stress, it does what?
Goes in the opposite direction.
It wants to undo the stress, right? Okay? So, what was the stress? What was the difference between this and this?
Higher pressure.
Higher pressure. So the stress was higher pressure. Okay? And so the reaction is going to shift in a way that will reduce its pressure, correct? Okay? Do you remember how that works? How you figure out which way it will shift to reduce the pressure? Do you guys remember that?
Well,
I'll do a guess it shifts right anyway.
like you said, if you add stress to the reactants, it
Depends on the stress. Because if I decrease the pressure here, it will actually shift left. But if we know based on the numbers here that it's going to shift right. Now I want to tie that back to what we talked about with Le Chatelier's principle when we said it will reduce its pressure when you increase the pressure because it wants to reduce its stress. So here's how we did that. I don't know if you guys remember. You count the number of gas particles. I've got 3 gas particles and a liquid particle. If I go from 3 gas particles to a more condensed liquid, I'm significantly reducing my pressure, correct? So what happens is when I increase the pressure, it says, hold up, I don't want that pressure. I want to relieve the stress. I want to reduce the pressure. So it's going to shift from 3 gas particles to 1 liquid particle to significantly reduce its own pressure. That's why it shifted which direction? Right. That's why the change in G was more negative. That makes sense? So I'm trying to connect what these numbers mean to the rationale with Le Chatelier's principle. Okay, that's what's going on here. All right, any questions on that? Okay, last thing, 797. I think this could be, have some significant meaning for you guys. I want to read it. I don't know if you guys will actually, if you actually read it all, so actually make sure we don't miss this. The meaning of change in G. I've kind of alluded to a little bit of this a second ago, but it's still it's still important. I think sometimes we know what like the sign means of change in G, but really truly understanding what change in G is can kind of be a pretty complicated concept. So this short section here does a pretty good job. So I'm going to read it, then we'll be done. In this section, we have learned to calculate change in G for a reaction under various conditions. For example, we just did a problem that showed that the formation of methanol from CO at 5 atmospheres with H2 at 3 atmospheres of pressure is spontaneous. What does this result mean? Does it mean that if we mixed 1 mole of CO with 2 moles of H2 together at pressures of 5 and 3, that we would get 1 mole of methanol? The answer is no. This answer may surprise you in view of what has been said in this section. It is true that 1 mole of methanol has lower free energy than 1 mole and 2 moles at those pressures. However, when CO gas and H2 are mixed under these conditions, there is an even lower free energy available at the system than having it completely react. So what they're saying here is, going from this to this lowers my free energy, but if I completely react it all, that's not the lowest free energy. When is the lowest free energy? When you're at equilibrium. And not necessarily is equilibrium fully to completion, right? So yes, we know that I'm going to produce more products because I'm going to have lower free energy when I'm producing this. But that doesn't necessarily mean the lowest free energy location is when I've completely reacted it all. Does that make sense? Okay, let's keep reading. The reaction stops short of completion because the equilibrium mixture of those guys exists at a lower possible free energy available to the system. To illustrate this point, we will explore a mechanical example. Consider balls rolling down 2 hills. In both cases, point B has lower potential energy than point A. Everybody see that? Okay? B is lower than A. In figure 17.7a, the ball will roll to point B. This diagram is, give us that word. You're not following. This diagram is analogous? I can't say that word.
Wait, where?
Third to last paragraph, where it says figure 17.7a. This diagram is.
Oh, I don't know that one. Analogous? No, analogous.
I know what they're trying to say, but I don't know how to say the word.
It's an analogy.
It's an adjective
Yeah.
form of analogy.
Yeah, it's an analogy of a phase change. For example, at 25 degrees Celsius, ice will spontaneously change completely to liquid water. Does that make sense? A to B would be going from solid water completely to liquid water. Like when we're melting something, we don't reach equilibrium at some point where I have a little bit of solid and a lot of liquid, right? At a certain temperature, it will all melt. Okay, so that is an example of something going all the way to completion. Does that make sense, everybody? Okay? Will change completely to liquid water because the latter has the lowest free energy. In this case, liquid water is the only choice. There is no intermediate mixture of ice and water with a lower free energy. The situation is different for a chemical reaction. In figure 17.7b, the ball will not get to point B because there's a lower potential energy at point where? C, like the ball, a chemical system will seek the lowest free energy possible. So B would be completion, but C is equilibrium. Does that make sense? Therefore, although the value of G for a given reaction tells us whether the products or reactants are favored under a given set of conditions, it does not mean that the system will proceed to pure products or remain as pure reactants. Instead, the system will spontaneously go to the equilibrium position, the lowest possible free energy available to it. In the next section, we will see that the value of change in G prime for a particular reaction tells us exactly where that position is. So, what I believe we're going to see is we are eventually going to switch this with K. Does that make sense? And under the conditions where equilibrium, when you're at equilibrium, your change in G is what? If you're at equilibrium, your change in G will be what? 0. So, if we wanted to find the equilibrium position, we could plug 0 in and solve for K. And then figure out what concentrations that would be. And that's what we'll do tomorrow. This will be our last lesson of this chapter. We kind of went slower through this chapter, but that's okay. I've been pushing you guys pretty hard. Any last questions? Thought we could give you a little bit more than that.